Today, we're going to cover related rates and other applications of derivatives. We'll start with the related rates. A related rate is how two quantities that are related, how their rates of change are affecting one another. For example, if you have a cube of side x and then the side gets bigger, how does that affect the volume of the cube? How does that affect the surface area of the cube? And so on. So if a cube has a side x, its volume is x cubed. X changes at a rate dx dt. So for example, the side of the cube can change at 2 centimeters per second. So it goes up by 2 centimeters per second. At what rate does the volume change? The rate of change of volume is dv dt. And dv dt is equal to, here it is, dv dt equals dv dx times dx dt. And this is called the related rate. This is the rate of change of volume and how it's related to the rate of change of side. So if the side is x and it changes at dx dt, then dv dt is dv dx, which is 3x squared from here times dx dt. So let's suppose we have a cube of 10 centimeters or any size, and its side is changing at 2 centimeters per second. So when the side is 10 centimeters, how fast is the volume of the cube changing? So dv dt is 3x squared dx dt. So you have 3, x is 10, you put 10 here, squared times dx dt, which is, and this is 600. So if the side is increasing at 2 centimeters per second, the entire volume of the cube is increasing at 600 centimeter cubes per second. So we're relating the rate of change of volume with the rate of change of x, which is the side. And that's what related rates are. Here's another example. Suppose you have a circle of radius r. When the radius changes, the area is going to change. Okay, so if the radius of the circle increases, so does the area. And then the bigger the radius, the bigger the area is going to be. Okay, how? Okay, dA dt is equal to dA dr times dr dt. dA dr is the derivative of a with respect to r, which we can get from here. dA dr is pi times the derivative of this, which is 2r. So this would be 2 pi r. So dA dr is 2 pi r times dr dt. This is the rate of change of area is equal to 2 pi r times the rate of change of radius. So when the radius increases, the area increases by this amount. We're going to do another application of related rates. I'm going to read this. Sodium chloride crystals can be grown, etc., etc. The shape of a crystal is given, the volume is given, and they're giving you the volume of the crystal, which is V equals square root of 3 x cubed over 3. It's over here. V equals square root of 3 over 3 times x cubed. And they want to know, find an equation for the rate of change of volume with respect to x. So they want the derivative of volume with respect to x. This is the volume of the crystals. That's what it is. And they want the derivative of v with respect to x. So dv dx is root 3 over 3 times the derivative of this with respect to x, which is 3x squared. The 3's will cancel, so that leaves you with root 3x squared, and that's the rate of change of volume with respect to x. Next, they want to know find the relationship between the rate of change of volume and the rate of change of the side. Okay. They want to know how is the rate of change of volume related to the rate of change of the side. dv dt is the rate of change of volume. dv dt is equal to dv dx times dx dt. dx dt is how fast the side is changing. Okay. So dv dt is dv dx times dx dt. We just found dv dx. dv dx is this. So dv dt, I'll put this in parentheses, dv dx is root 3 times x squared. And that's it. This is how the rate of change of volume is related to the rate of change of side. So when the side changes by this amount, the volume will change by this amount. And then in part C, they're giving you an example. They're asking you, when X, the side, is 3 millimeters and the crystal is growing at 9 millimeter cubes per day, what is, here it is, the side is 3 millimeters, the rate of change of volume is 9 millimeter cubes per day. How fast is the side changing? This is the side of the crystal. So the rate of change of volume is dV dt, that's this quantity. So I'll put 9 there, equals root 3 times x squared would be 3 millimeters squared times dx dt. Dx dt is what we're looking for. So 9 equals root 3 times 9 times dx dt. Now we're going to solve for dx dt. So you divide 9 by 9 root 3 and you end up with the side is going to change at a rate of 0.577 millimeters per day. So if the volume increases, the side increases by this amount. The side of the crystal will increase by this amount. We're going to do another example. This is a Cepheid. A Cepheid is just a variable star which pulsates radially with variable brightness. They're telling you the story of the star here, and I'm going to give you the equation for brightness. The equation for brightness of this star is 6.5 plus this quantity here. And what that means is when you look at that star, the brightness is going to change every day. And it's going to change according to this function. So sometimes it's brighter, sometimes it's less bright. And it's according to this equation. And if you wish to figure out how bright it is during any day, T is in days. So you just substitute the day number here and it'll tell you how bright, you can calculate how bright it is. They want the equation for the rate of change, and they also want the rate of change at 3.75 days. The rate of change of brightness is how does brightness change with respect to time. That means the derivative of B with respect to time. This is the function B. We need to differentiate it with respect to time. 6.5 gives you 0 plus 2.5. The derivative of sine is cosine 2 pi t over 3. All of this times the derivative of 2 pi over 3 times t is 2 pi over 3 times 2 pi over 3. Simplify this. 2.5 times 2 is 5 pi over 3 cosine 2 pi over 3. So this is the rate at which the brightness of the star is going to change, the rate per day. They want to know at 3.75 days, what is the rate of change of brightness? So what do? You put 3.75 here for t in the equation for rate. So that gives you 5 pi over 3 times cosine 2 pi over 3 times this number, 3.75. And when you calculate this, you get 0 units. It means on that day, 3.75 days, the brightness does not change at that moment. It doesn't change. So the change is 0 units. That's what 0 units means. So again, this is a star which pulsates radially. Its brightness changes according to this equation. They wanted to know the rate of change of brightness. We got it by taking the derivative of this with respect to time. Then they wanted to know at t equals 3.75 days, what's the rate of change? So you substitute 3.75 days there, and that'll give you the rate of change. We're going to do another example, this one. The displacement from equilibrium of a mass in simple harmonic motion is given by, and I'll write it bigger in here. Simple harmonic motion is when you put a mass at the end of a spring and you pull it and you let go of it, and it'll do this. So the equation of motion is given this: 10 cosine 11.9 t minus 4 sine 11.9 t. What they want to know, at t equals 0, where is the mass going to be? Y is the position of the mass. So you substitute 0 here and 0 here. That will be 10 cos 0 minus 4 sine 0. Sine 0 is 0. Cos 0 is 1. So this is 10 times 1, which is 10 centimeters. So the mass is at 10 centimeters from equilibrium. They also want to know where is the mass at t equals 0.1 seconds. So for part B, they want at t equals 0.1 seconds. So you substitute 0.1 seconds here. Okay, y of 0.1 is 10 cosine 11.9 times 0.1 t minus 4 sine 11.9 times t, which is 0.1. Make sure you set your calculator to radians, okay, to do this. So when you calculate this, you can use a calculator if you wish. You end up with 0.003 centimeters. That's what happens at 0.16. Then they want to know what is the velocity of the mass at t equals 0. Velocity is the rate of change of y, derivative of y with respect to time. So now we need to take the derivative of this. It'll be 10 times the derivative of cosine is minus sine, so that gives this minus sine times 11.9. So minus 10 times 11.9 sine 11.9 t minus 4, and then the derivative of sine is cosine 11.9 t times the derivative of the inside, which is 11.9. That's why I put the 11.9 in front. Okay, when you substitute t equals 0, sine of 0 is 0, so this entire first term is going to be 0. Minus 4 times 11.9, which is 47.6, times cosine of 0, which is 1. So the answer is negative 47.6 centimeters per second. This is the velocity of the mass at t equals 0. So for displacement, you substitute directly in the equation of y. For velocity, you take the derivative of y with respect to t, and then you substitute the time that they gave you.